Okay, so we're continuing 4.5, which is modeling with exponential and logarithmic functions. This is the last section in chapter 4. Did I code the sample test, actually? Yeah? Okay, so we will have a test next Wednesday. Yeah? And Monday, I'm not going to be here. So Monday, October 31st, I'm not going to be here. This is this is for fun, so I'm not sick or anything. Yeah. Okay. So this is one of the days that I get to take day off. That's it. Yeah. But I'm not going to do that anymore. So that's the only one this semester. Now let's continue with exponential decay. Yesterday we did 2 examples of exponential growth, right? So we're going to do exponential decay right now. Yeah. And later on, we will talk about Newton's law of cooling, and we will talk about logarithmic scale, which is pH, the power of hydrogen. And there is also the Richter scale for the earthquake and decibel scale for the sound, intensity of sound. Yeah. So it will be quite an exciting day because you get to see how it is used in real life. Yeah, this is exponential decay. We use it in real life. Yeah. All right. Let's start. Share the desktop. Okay. So journal or OneNote. And math to 60. Okay. Oh, good. We're here. This is the last. So we talk about two examples of exponential growth. Now, pay attention to the second example here. Yeah. For the second example, it says doubles every 30 minutes. So after 30 minutes, the amount becomes 3,000 instead of, when previously it was 1,500. So on your exam, I will of course have something like this. So the most important thing is to be able to translate what does it mean doubles every 30 minutes. So this is the translation. Yeah. All right. Now it's the next one. So B. This is still exponential. So exponential growth. Exponential growth. All right. Oh, decay. What am I saying? I just said decay, and then I went back to growth. Okay. Well, what decays exponentially? So, radioactive substance. Yes. So this is the most common, radioactive substance. Decay exponentially. All right. What is considered radioactive substance? Well, substances that are not stable. You know, we have carbon-12, right? Maybe I should write carbon-12. So carbon-12, this is stable, so it doesn't decay exponentially. But for example, something like carbon-14, this is not stable, so this is radioactive, so this is the one that decays exponentially. What else? Strontium. Alpha, beta, gamma particle, what is plutonium? So those things are considered radioactive substance. Yeah. Now, remember we had an earthquake in Japan recently? Well, when was that?
3 or 4 years ago.
Yeah, 3-4 years ago. And then there's a nuclear reactor that is affected by the earthquake. Yeah. So of course, if you have a nuclear reactor, what's inside a nuclear reactor? Radioactive substance. Yeah. So it's going to take thousands of years for the radioactive material to to be considered gone. I mean, they're not going to be completely gone, but to be considered gone, but it's going to take thousands and thousands of years. Chernobyl, 1986. Yes. It's going, yes, 10,000 years. You're right, because radioactive substances are dangerous. You know why? If it's not stable, then it tends to bind another atom, yeah, in your body. And then so your body, the atoms on your body is no longer stable, and it affects everything: your brain, your blood, your digestion, everything. So Chernobyl, you said, 1986, right? 1980s, I remember. Yes, 1986. I remembered. I saw the explosion on the TV, and then you said 10,000 years. That's about right. So that area will become inhabitable for 10,000 years, years and years and years. Yeah. Now, the other thing that we use this exponential decay model is to do carbon dating. So have you ever heard of this? Carbon dating. What is carbon dating? Oh, I'm dating carbon.
Is that where they like take a sample or something and they test how old it is from being under the ground?
There you go. So what you do while you're dating the carbon, it's basically identifying the age of a fossil, yeah, based on the content of its carbon. Because we know, well, we will talk about half-life. We know the half-life of a carbon 14, and then we compare it with the amount of carbon 14 in living things. So, for example, if you find a fossil of leaf, so what do geologists do? How do they know? Oh, this is 5,000 years ago, or this is 7,000 years ago. So what they do is they take a sample of the fossil, of the leaf fossil, and then measure the amount of carbon inside. So I asked Dr. West, he teaches geology. Hey, Dr. West, how do you actually, is there a machine that does carbon, that measures the carbon? So he explained to me a little bit, yes. So there's a machine that can tell us the carbon content of a fossil or anything. So then they compare it to the carbon content on the real person. So if you have a mummy, right, that's how they determine the age, by doing the analysis of carbon content. And we call that process carbon dating. Yeah, so it's used. It is being used. Yeah, so these are applications. Now, for example, okay, what is Pu? Is it plutonium? Do you know what this? So this is. I'm going to write. This is 1986 Chernobyl. So this is a power plant, nuclear power plant in Russia. Yeah. What is Pu? Is it plutonium or? Can you guys Google what is Pu? This is the chemical. And then, oh, that's true. But Wi-Fi. Let's see. Google Wi-Fi. Oh, maybe I'll Google here. Okay, what is it? What is Pu? No, you won't be able to. Plutonium? Yes. Okay. So plutonium. So 239 Pu. This is radioactive, and this is plutonium. Is very often used in nuclear power plant. By the way, do you know why people have nuclear power plant even though it's dangerous? What is it?
Because of how much power and how long it's
right. Right. It is cheap. So the power that is nuclear power plant is the cheapest power plant, the cheapest way to generate power. Yeah. You know what other power plants we have? Wind. I mean, wind. You know, it's not. I mean, it really depends on wind. What else? Solar. You know how much solar cells you need. Water, right? Nuclear is the cheapest one. That's why even though it's dangerous, we still have it, because that's the cheapest way to generate huge amount of power. Yeah. Now, the Chernobyl is a small city, a small village in Russia, and which has a very powerful nuclear power plant, and then in 1986 it blew up. For some reason, the nuclear reactor got so hot or something, and then it blew up. Yeah, because it produces way too much power. And you know, this plutonium has a half-life of approximately 24,360 years. So what do I mean by has a half-life? Well, I will write down the definition later. So after 24,360 years, the amount becomes half. Wow, so you can imagine how long does it take to clean all those nuclear, right? Because the amount becomes half of it after 24,000 years. Yeah? Okay. Well, another one is strontium 90. This is also radioactive material, but it only has a half-life of 90 days. So it really depends on the radioactive material, the number of, yes, half-life, yeah. But strontium, we don't use it in nuclear power plant. This one is used in nuclear power plant. So that's why nuclear power plant is dangerous if it leaks, yeah, because it's going to take 24,000 years for the material to become half of the original amount. Yeah? Okay. Now, let's talk about the model a little bit. I really like this exponential growth decay. That's why I talk a lot about it. But anyway, I want you to know how it's used in real life and not just learn log as log, exponential as exponential. We use it. Yeah, there are exponential decay, there's exponential growth. Now, same thing. The model is m of t, or n of t is m naught e to the rt. Is it the same as the exponential growth? Yes. What's the difference? R must be less than 0. Yeah, the rate, the relative growth rate. So remember R. Can we say what is m? What is m of t? Maybe let's define it again. So m of t is what is m of t? The amount of material at time t of a radioactive substance at time t. All right. What is m naught? Can you tell me? Initial amount. And what is R? R is the relative decay rate, right? And R must be less than 0, otherwise what? You have exponential growth, yeah? So R less than 0, we have decay. And if R is greater than 0, we have growth. So the same model, just the value of R, yeah? All right, so now I already mentioned half-life, but let's write down the definition. What is half-life? Half-life is the reciprocal of doubling time. Do you know what doubling time means? What does doubling time mean? Times to double. Time it takes for an amount to double. Half-life is time it takes for an amount to become half of the original amount. Yeah, so that's what I'm going to write down. So half-life is the time it takes for a mass to decay to half of its original amount. All right. Yes? So you can think of half-life as doubling time, but instead of doubled, it's going to be half of its original amount. All right. So, okay. Now, I could give you the formula for R. Yeah? Okay. When next page. I'll wait for you. Finish? Okay, so what is the formula for, I don't think you have to memorize this, but it might, or maybe you don't. So let's just do example. Page 380, number 14. So that's what I wrote on my book. 380, number 14. All right. Are you guys ready? Yep. All right, good. So, for example, this is page 380, number 14, so you could look it up later. Okay. The half-life of radium-226 is 1600 years. So suppose we have 22 milligram sample. So this is a very small amount. Okay, 22 milligrams. A, find a function that models the mass remaining after T years. All right. So suppose the half-life of radium-226, radium is Ra, is 1600 years, and we have 22 milligram sample. Find a function that that models the mass remaining after 2 years. So what happens after 4,000 years? So B, how much? Well, we could deal with it later. Of the sample remains after 4,000 years. So how would you do this? What is given? Yes, so half-life. How do you translate this? Okay, so this is like the one we did before. It doubles in 30 minutes. So what is it? M of, so let's write down the formula first. M of T is M naught E to the RT. Now, do you care if I use N or P or Y? No, they're all the same. Yeah, so it doesn't matter. Now, M of what? 1600 is equal to half of M naught, or 11. Yes, you're right. So if you say that M naught is 22 milligrams, so that's the initial value, and then this one is just half of M naught, which is 11. You want to put 11 here? Yeah, we can. 11 milligrams. Half of it. Yeah. So this is something like the doubling time that I show you earlier. This is something in which you need to be able to translate. Yeah. Okay. Now, so let's solve for. So basically, what you need to do is solve for R. So that's what we want to do first. Because I have M naught, I just want to solve for R. Yes. Okay. So M of T is equal to M naught. Oh, I know M naught, don't I? What is M naught? 22 E to the RT. Well, what is M of 1600? Is 22 E to the R times 1600. Okay. And then I'm going to put, what is M of 1600? 11 is 22 E to the 1600 R. Okay, good. Then what? How do you solve this? isolate the exponent. So half is equal to e to the 1600r. Okay, then ln both sides? Yes. So, okay, I don't have space here, so I have to do it here. Yeah. So 1600r, no, ln half. So ln half is ln half is equal to 1600r times ln e. What is ln e? 1. Okay. So what is this? R divided by 1600. Yes? All right. So what is R approximate? Or, well, we'll just leave it the way it is. Yeah. So this is the model. M of t is equal to m naught, 22 e to the ln half divided by 1600 times t. Alright, so this is your model. Alright. Now, there is a shortcut formula to get the R if you have the half-life. Yeah, so I'm going to write the formula. This is ln half divided by a half-life is equal to R. So this is a shortcut formula if you want to use it. Yeah, because it's going to happen again and again that that it's true. Yeah. Good. Now, can I answer? Is it okay? So how do you find R? It's just ln half divided by half-life. So it's easy. Rather than doing all these, right? So you just get the R by ln half divided by half-life. Yeah. All right. Good. Are we okay so far? Mm-hmm. Now, this is a question. How do I answer my B? What is M of 4000? Mm-hmm. Right. So that's equal to 22e to the ln half divided by 1600 times 4000. Okay. Okay. So you could just get an approximate value. Let's use our calculator now, and then make sure we could use our calculator. Alright. So what is this? So 22 multiplied by e to the ln half ln 0.5 divided, so you got to be careful here, divided by 1600 times 4000. Okay. What is it? 3 points. Let me do it again. So 22 times e ln 0.5 divided by 1600 times 4000. Yes. What is your answer? Come on, try it using calculator. 3.889. Yes, that's right. 3.89. Yes. So after 4,000 years, we still have 3.89 milligrams. Yes. So after 4,000 years, 3.89 milligrams. Wow. So it does take a long time, right? So this is after 4,000 years. it starts with 22 milligram after 4,000 years, you still have approximately 4 milligrams. But I'd like you to enter it on your calculator and make sure you could do it. Yeah, can you try on your calculator, please? Yeah. Let's see Wi-Fi here. Elect faculty. Yeah, that's right. Did you guys get it? Okay, good. All right, now the next question is, after how long, okay, well, when you're done. So the next question is, after how long, so C, are you guys done? Should I go back? Done? Okay. So after how long will only 18 milligrams of the sample remain? Okay, can you try to answer this question? So again, this is the model. MLC is equal to 22 E to the ln half over 1600. Can you try to answer this question? So what is being asked? P. What is given? MLC is equal to 8. Okay. Can you please try it? Yeah. So I'll discuss it in a few minutes, okay? Let me find out another example of, let's see, mummies. Okay. Finished? What's the answer? How long? What is it? 463? Did everybody get the same answer? Okay, 2 more minutes, right? And then I want to discuss Newton's law of cooling. So it's interesting also. And we use it. If you say, do we use it? Yes, we do. But actually, let's do one carbon dating. Okay, so actually, how are we going to do this? 18 is equal to 22 e to the ln half over 1600 c. Okay, good. Now what? Same thing, divide by 22. So we need to isolate always. So what is 18 divided by 22? 9 over 11 is e to the ln half over 1600 t. Then what? ln. So once we finish isolating, then it's ln. So ln 9 over 11 is equal to ln half over 1600 t times ln e. Okay, good. ln e is 1. Okay, good. Now, how do I solve for t? So, what are you going to do? Divide or multiply? Multiply, yes. Because it's scary, right? If you divide, look at this. If I divide by ln half over 1600, look, it's scary. Isn't it? Yes. So we're just going to multiply with the reciprocal, which is 1600 divided by ln half, both sides. So 1600 divided by ln half. So what is t equals to? Well, then this one we need to use calculator, don't we? Yeah, okay. I don't know what it is. 1600 multiplied by ln 9 over 11 divided by ln 0.5. So I'm just going to put ln 0.5. Yeah. 463? Okay, so your answer is approximately 463 years. Good. Finish. Are we okay so far? So expect something like this on your exam. Yeah. Do we want to the example of carbon dating? So we talk about mummies. Maybe we do one? Okay. Let's see what number it is. I found one. Oh, okay. Number 22. Okay. This is page 380 or 381? The 381, number 22. Yeah. All right. So the second example is page 381, number 22. Okay. So the burial cloth of an Egyptian mummy is estimated to contain 59% of the carbon-14. So this is the radioactive carbon that I was talking about previously. Carbon-12 is stable, but carbon-14 is radioactive. Yeah. It originally contained. Okay. How long ago was the mummy buried? So this is the type of question. Yeah. So, I have to give you the half-life. The half-life of carbon-14 is 5,730 years. All right. Question. Okay, so how would you do it? First of all, we will find what? R? Okay. Do you remember the formula? ln half divided by half-life, right? So I'm not going to give you the formula, yeah, ln half divided by half-life. So you need to remember. So ln half divided by 5730. Am I going to evaluate it? No. I'm going to use the exact value. Now, in Math Excel, please use the exact value and then round at the end. Because otherwise, it's probably going to differ 1 decimal or 2 decimals, yeah? So, and you're going to get, it's wrong, yeah. So, what is my model? M of t is, so first of all, we will write down the model. M of t is equal to m naught e to the what? ln half over 5730 t. Are we okay so far? So we always need to write the model. All right. Good. Now what? %. So what does it say? The burial cloth of an Egyptian mummy is estimated to contain 59% of the carbon-14 it originally contained. So, what was that? How am I going to use it? So it's 59% of its original. So how do I write that? 0.59 times the original, right? All right, so this is 59% of the original. E to the ln half over 5730t. Okay, so we just have to solve it, don't we? So cancel out the MO, M naught, divide both sides by M naught, and then what? ln. So it's pretty similar. So ln 0.59 is equal to ln half. I'm going to put ln 0.5 divided by 1600 t times ln e. Are we okay so far? Maybe it's easier if I put my ln here. Say it again? Oh, because I made a mistake. Thank you. It's not 1600. 1600 was the previous problem, right? Yeah, not this one.
Why am not on the other side of this equals symbol?
Oh, why do I have M naught here?
Yeah.
Because it says 59% of the original. So it's 59% of original, right? So it is 0.59. What was the original? M naught. Yes, that's why. And then we divide both sides by M naught. So I skip this step. Let me write it then, because it's clearer, I guess. This is what I did was divide both sides by M naught. So I just cross it out. You see? Is that what you're asking me?
Yeah. Okay.
Maybe I should write it this way, right? So it's 0.59 is equal to E to the ln half. Oh, 1600 again. Oh, bad habit. ln half divided by 5730t. So then you take ln both sides. I'm sorry, I should have written this one. Yeah, instead of just crossing the ln, the m naught. Are we okay? Yes, Josh. Mm-hmm. Yes, because it says 59% of its original amount.
Yeah, I didn't see the M of T, so.
Oh yeah, this is M of T. which is, it says that the amount at this time is 59% of the original.
So T equals
0.59 m naught. Yes. So maybe I should write down m of t is equal to 0.59 times m naught. Yes, you're right. Perfectly correct. Yeah. Yes. Yes. Good. Good point. I should have written that down. I'm glad you asked. I think everybody else has the same question too, right? You see, it's good that you asked. So add these. So ln E is 1. Then how do you solve for t? Multiply by 5730 divided by ln 0.5. 5730 divided by ln 0.5. All right. Then these cancel. What is p equal to? What did you say? 4,362? 60? Huh? 61? Okay. 4, 3, 6, 2, 1, 2. 2 or 1? Okay, good. So it's 4,362 years ago, right? So answer. How long ago was the mummy buried? It's 4,362 years ago. Wow. Okay. This is how they, like scientists, geologists, archaeologists, this is how they tell how old a mummy is. Yeah. All right. So that's how they tell. Otherwise, how do we know? Right? Truthfully? Yeah. Are we okay so far? Okay. So now the next one is, I'm done with the exponential growth. Now the next one is Newton's law of cooling. Okay. Let's just say you have soup. What soup do you like? Chicken noodle soup. Yes, I like that too. Yes. I just cooked chicken noodle soup, and I want to let it cool down. Is it easier to cool down if I put it inside my fridge or outside? Inside my fridge. Why? Because your fridge is colder, and it will make your chicken noodle soup cooler easily. That's true. Yes. So what we meant to say was the temperature depends on the surrounding, right? Okay. So this is what the Newton's law of cooling is all about. So the rate of cooling of an object is proportional to the temperature difference between the object and its surrounding. Yeah. So I'm going to write that down. Okay. All right. This is also exponential, and is it applicable to real life? Yes. Yeah. So all the applications that we discussed are real life applications. So the higher level, the math you take, the applications is becoming a little bit real. I mean, more real and more real. Yeah. You could see it used in real life. Yeah. So the rate of cooling of an object, is proportional to the temperature difference between the object and its surroundings. By the way, you'll see the same thing, Newton's law of cooling in calculus. Yeah, so that's why I'm discussing this. I remember now. All right. So there is a section using Newton's law of cooling. Yes. So P of T, this is the formula. I'm going to write it for you. Is Ts plus D naught e to the negative k2. Alright. So D naught, this is, if I have a naught, what does it mean? Initial. I don't know why the book uses D. Hold on, let me find out, okay? Because I thought I used T. Hold on. Yeah, they use D naught. Yeah, they don't use T here. Yeah, D naught is the initial temperature. So anything with a naught means initial. Yeah. What do you think Ts would be? Surrounding temperature. You're right. What is K? This is a positive constant depending on the object. So that's why I put there is a negative here, and the K must be positive depending on the object. What is P of T? Is the temperature at time T. At time T. So this is actually an exponential decay model, but what is the difference? This. So you have this. So you're adding. So you're adding the surrounding temperature, right? That's the only difference. So it's like shifted. Oh no, this will be exponential decay. Yeah. So it's the K is always positive, but it will be an exponential decay. Yeah. So there is the difference. Yes. Now I was looking at number 384. So page 381, number 24. Sorry. 381, number 24. Oh, this is we're doing the, what is it, NCIS job here. Okay. So Newton's law of cooling. Oh, let me write down what it is, because this is pretty interesting. Page 384, number 24. So Newton's law of cooling is used in homicide investigations to determine the time of death. Do you guys watch NCIS? Who is doing the, is it Duck? Is it Ducky? Yes. Yes. The time of death. Okay. The normal body temperature is what? That's right. Is 98.6 degrees Fahrenheit, right? So immediately following the death, this is sort of interesting. The death, the body begins to cool. So it has been determined experimentally that K is equal to 0.1947. 1947. So K is a constant, and it depends. For body, it's 0.1947. For soup, it's different thing. Yeah, but for body, it is 0.1947. Now, this is time is measured in hours. Yes. So suppose the surrounding temperature is 60 degrees Fahrenheit. What is the initial temperature? 98.6. Yes. What's the surrounding temperature? Okay, 60 degrees Fahrenheit. Yes. All right. A. Find a function P of T that models the temperature T hours after birth. Alright. I think you guys know because everything is given. So, what is the formula? T of T is Ts plus D naught e to the negative kt. Yes. Good. So, do I know surrounding temperature? Which is 60. Do I know D naught? 98.6 e to the negative 0.1947. Yes, that's your model. Yeah. Okay. Now, so if the temperature now is what? Is 72 degrees Fahrenheit. How long ago was the time of death? Okay. So, what are you going to do here? What is given here? 72 degrees. That's right. T of T is 72 degrees, right? So we have 72 is equal to 60 plus 98.6 e to the negative 0.1947. Okay, what am I going to do now? What do you do? You subtract 60? Okay. So that's easy, you just subtract 60. So 12 is 98.6 e to the negative 0.1947 t. And then what? Divide both sides, 98.6. Right? Okay. So, and then we take L on both sides. So 12 over 98.6 is equal to e to the negative, I have no space here. And then we take L on both sides, is it? Okay. Oh, I have to go down a little bit, sorry. So we take L on both sides, then what? Yeah, ln 12 over 98.6 is equal to negative 0.1947 t ln e. Oh, t. And ln e is 1. So divide both sides by negative 0.1947. What is t approximately? That's my calculator. ln 12 12 divided by 98.6 divided by 0.1947. Oh, is it negative? Hold on.
10.9.
But how come I get negative? Hold on. Oh yeah, it is. I have to divide both sides by negative, yes. So 10.87? 10.9? Yeah. So approximately how many hours ago? Yes, so approximately 11 hours ago. Wow. We are detectives. Yeah. Are we okay so far? Okay. Do one more? Yeah. The next one is turkey. Turkey, gobble, gobble. All right. Yes. Is it interesting? All right. Now, you know why the applications in algebra is not as interesting as this? Because the algebra part is simple, right? But once you learn a little bit higher level, the applications can be interesting. Because it's very, very applicable. Don't you think? Mm-hmm. Now, the next one is turkey. Yes. So this is Halloween, Thanksgiving turkey. So, roasted turkey is taken from an oven. When its temperature has reached 185 degrees Fahrenheit. Is that the temperature you guys cook your turkey? So, oh, okay. But don't you leave it to cool down a little bit or no? Why do they want to take when the temperature has reached 185 degrees Fahrenheit? The interior temperature of the turkey, right? Yes. Yeah, that means it's cooked, right? Yeah. Yeah, I remember. Yeah. I used to cook turkey a long time ago, but now not anymore. And it plays, or maybe this year I will, on a table room, in a room where the temperature is 75 degrees Fahrenheit. Is this something real? Is this what we do? Yes. So this is going to happen during your Thanksgiving. Yes. All right. Now the question is, if the temperature of the turkey is 150 degrees Fahrenheit after half an hour, what is its temperature after 45 minutes? Aha. All right, but this is easy, right? You can do it. So that's what we want to know. Yeah. So should we leave the turkey out for 45 minutes or more, or less? Yeah. So this is the thing. So what is given? Do we know the formula? P of T is equal to Ts plus D naught e to the negative kt. So do we know Ts? Yes. Yes. 75 plus D naught 185 e to the negative KT. So this is the formula, and I don't know what K is. That is the first thing that I need to solve.
If we're looking for a temperature, would it be 150 E, not 185?
150, no. 185, you mean this one?
Yeah.
185 is the initial temperature.
Oh, yeah.
Yeah. Uh-huh. It's okay. So yes, D naught is initial temperature. Yeah? All right. Now, what is this? It says the temperature is 150 after half an hour. How do I write that? T of 30 minutes? So now we're talking about minutes, right? Is equal to 150, and then you need to find T of 45. Yes. I think we can do it. How do you do it? Find K first. Yeah. So T of 30 is equal to 150. So we have 150 is equal to 75 e to the negative k times, what is T? Oh, I forgot. Yes. Plus 185 e to the negative k times 30. Yes. Okay, so we could solve for k. Okay. So Alex, you're okay?
I'll figure out something.
Oh, no. What we did here
Yeah.
was substitute the 150 here as T of T. And then this is your T. Your T is 30. Got it? Yeah. No, you could ask all the time. Yeah. Is it okay, everybody else? So what do you do? 75 is 185. Oh, this one you guys can do it. Then what? Divide by 185. Okay, cool. So can we actually reduce 185? What is it? Thank you. Can we solve for K? Well, of course. We have done this how many times? Many times, right? So you see, once we do something many times, you become more and more comfortable doing it, even though it looks complicated. Yeah. ln 15 over 37 is equal to negative 30k ln E. And now, even if I wake you up when you sleep, I ask you, what is ln E? 1, right? You'll know, hey, somebody's sleeping. Wake up. What is ln E? You probably know exactly it's 1. And then divide by negative 30. Both sides. Yes? So that is your K is ln 15 over 37 over negative 30. All right. So what is your model again? T of P is equal to 75 plus 185 ln 15 over 37 T. Oh, over 30 times T. All right. So can we answer the question? What is P of 45? We will just substitute. Right? 75 plus 185. By the way, where did the minuses go? I don't see the minus. They cancel out? Okay, good. 75 plus 185 ln 15 over 37 over 30 times 45. These are all the exponents. What is P45? So it is 75 plus 185 times ln 15 divided by 37 divided by 30 times 45. Oh, mine is syntax error. Hold on. Let me see. 185. Oh, I know why. Okay. So 75. Hold on. 75 plus 185 raised to the ln 15 over 37. Oh, I forgot my e? Oh, no wonder. Okay. Yeah. So 75 plus 185 times e to the ln 15 over 37 divided by 30. And then we multiply by 45. Let me see. Close parentheses. Right. What is your answer? 122.75. Yes. So after 45 minutes, the temperature is 122.75. So after 45 minutes, it is 122.75. What is the unit? Degrees Fahrenheit. Okay. Doable? Okay. So on your next exam, expect a few applications. Yeah. I'm not done. I'm still not done with the logs. So tomorrow I'm going to continue with the logs. Yeah. So we will talk about pH, and that's fun, and Richter scale and decibels. All right. What homework's due tonight? No, not for 4.5. 4.4, yes. How about 4.3? Already due? Okay. All right, so just 4.4. Okay? Okay, guys, see you tomorrow, but we will still do 4.5. It is long. Yeah, I just want to talk about the application so you know how we use it. Hold on. What did you say? The first is Wednesday next week. Maybe Tuesday next week. I won't have time this week. Yeah. No, for example, Tuesday next week. Yeah. Yes, that's the last step. I haven't given back. I still have it with me. I haven't finished grading. I was just using it. Yeah. Okay. Okay, so we'll see you tomorrow. Continue. Okay, so we're still continuing with the modeling with log functions tomorrow. Yeah.